Hi everyone, I'm Jiahui. I'm going to talk about new approaches for quantum copy protection. This is joint work with Scott Aaronson, Qipeng, Mark Zhandry, and Ruizhe Zhang. As we know, quantum information cannot be copied in general. Given an arbitrary unknown quantum state, the operation to turn it into two states identical as the original one is non-linear and not allowed by quantum mechanical principles. Inspired by such property, people have tried to come up with cryptography constructions which are only realizable in the quantum world and not meaningful in the classical setting. For example, quantum money is one most famous application brought up by Wisner 40 years ago. In the setting of quantum money, a bank wants to encode some value of money into a quantum state, and any user with such a quantum state can come to the bank to verify it and spend it. However, the user is not able to turn this state into two banknotes that also have the same money value. And in the Wisner setting, the banknote can only verified by the bank itself. And later on, people have tried to come up with public key quantum money schemes where the note is generated by the bank, but everyone can verify whether this money state is a valid one. And we also ask the question, if we can extend such encoding of information from just value to functionalities. In a paper by Aaronson in 2009, he brought up the idea of quantum copy protection for softwares. The idea is that we have a classical functionality F, and we have this procedure of program generation that we generate a quantum state which allow us to compute on any input that evaluates to the same output as the original function with almost one probability. However, a user holding such a state is not able to turn it into two states that also compute the function. In this paper, Aaronson also gave the first construction. This is a construction for any unlearnable functions relative to a quantum oracle. We'll specify what unlearnable and a quantum oracle means. And so here we just mentioned that quantum oracles are hard to implement even when we consider cryptographic heuristics. So what's an unlearnable function? Consider a learning game where we have a quantum polynomial time adversary, and we have the functionality it wants to learn as a black box. The adversary can query this black box for polynomial many times and get responses. Afterwards, it produces a program that it claims to compute the function. This program, we can consider it as consisting of a unitary and a possibly mixed state. Then the challenger tests whether this program evaluates to the original functionality with a large enough probability. Such a threshold probability, here we call gamma, is chosen by the challenger, and it depends on the family of functions we're considering. An adversary wins if its program passes such a threshold. And the family of functions is said to be unlearnable if any QPT adversary can only win with negligible probability. Next, what's a classical and what's a quantum oracle? A quantum oracle is a unitary that you can access in a black box way, and it can perform functionalities of any quantum circuits. It can be heuristically implemented by VBB obfuscation of quantum circuits. For those who are not familiar with the notion of VBB obfuscation, you can just consider it as a cryptography primitive that is indistinguishable from accessing an oracle. Similarly, a classic oracle are unitaries that implement functionalities of classical circuits. It can be queried in superposition by any quantum adversary, and it can be heuristically implemented by VBB obfuscation of classical circuits. Even though VBB of classical circuit is already a very strong assumption, VBB obfuscation of quantum circuits is this even stronger assumption where, to our best knowledge, there's no positive result known. Therefore, the paper by Aaronson 2009 asks the question that if we can obtain a classical oracle construction for copy protection. Next, it comes to our results. We divide our results into 3 parts. The first is definitional works. We give a meaningful physical procedure to test quantum programs in a game-based definition for copy protection security. And second, we answer the previous open question with a positive result. We can construct copy protection scheme for any unlearnable functions relative to a classical oracle. And finally, we state there's some barrier discussed by a concurrent paper in the plain model to do copy protection for any unlearnable functions. And then we weaken the security notion, and we discuss the construction for such weakened security notion called copy detection. So here we give a definition for copy protection. We have this setup algorithm that generates a secret key. And then there's this generate algorithm that takes in the function you want to copy protect and the secret key to generate a copy protection program. So throughout the slides, we will represent any quantum program as a unitary and a quantum state. And this unitary may include some classical functionality and also some classical information that gives you instructions on how to run such a program. And finally, we have this eval algorithm that basically just runs this unitary on the input state and the input X you want to evaluate, and finally measure the last output register. And also it outputs the leftover state that you have run once. Here notice that our eval algorithm is actually just a universal quantum circuit that runs any input unitary and quantum state. We stress this because later on we will emphasize this difference in our eval algorithm and in weakened security notions. So here we give an attempt definition for security. Why is it an attempt? We will specify later the issues with such a security definition. So for correctness, of course, we need to evaluate correctly on all inputs with almost 1 probability. And for anti-piracy security, we want that any QPT adversary, when given 1 copy of the honestly generated copy protection program, it is not able to produce its 2 other programs described by U1 and row 1, U2 and row 2, such that both of these programs can pass the test if we sample random inputs according to some input distribution correlated with the function family, and they compute correctly, both with a probability larger than gamma. And we say adversary wins if they pass such a test, and we want no QPT adversary to win with non-negligible probability. And note that when we test the quantum program, we do not have to follow instructions given by the authentic program. And this is a difference from copy protection and later other weaker security notions we will discuss. However, there are issues with such a security. The issues lie in testing the quantum program. So how do we estimate the success probability of quantum programs? First, on the operational level, it is very intuitive how we test a classical program. We just run the program a few times on random inputs sampled from the function's input distribution, and then we estimate such a probability. However, for quantum program, we cannot assume that, like the honestly generated programs, the adversary's pyro programs may not be able to do gentle measurement and be run many times. Maybe after we run it for once, it may destruct. And another issue is in the physical level. So consider a pyro program that is a superposition of a good program, which always outputs the correct output, and the dummy program, which just does dummy guesses. Should we label this program successful or unsuccessful if it's an equal superposition of good and dummy? If we're able to label it, we're able to distinguish such a program from a good program or from a dummy program. And this is distinguishing two unorthogonal states. And we know that this is not doable if we're only given one copy of such a state. Unless we're given many copies, we are probably able to distinguish them. However, here in this security game, this game-based security game, we're only given one copy of each Pyro program. And next, we give an example. So here, an adversary produces two Pyro programs. We say the P1 in the first register and P2 in the second. And these two programs are entangled in a way that with epsilon probability, which is a noticeable large epsilon, we get both programs as good. And the rest of the cases, we get both programs as dummy. So the probability that we get good is noticeable, and this should be considered a successful attack in some settings. How do we capture such a successful attack? So to properly test quantum programs, we define a measurement procedure with the following properties. So the measurement performs on a quantum program and outputs a probability and the leftover program P prime. The condition on the above procedure outputs probability P. The leftover program would also pass the test with probability P. Such a procedure can be implemented with approximation efficiently, and the techniques are inspired by witness-preserving QMA amplification by Merritt-Watrous and quantum traitor tracing by Zhandry in 2020. Afterwards, we can properly define if an adversary wins. So at the beginning of the security game, the challengers first set the threshold probability gamma, which depends on the function family we are copy protecting, as we discussed beforehand about the unlearnability of the functions. After the adversary has produced these two Pyro programs, we apply the measurement procedure respectively on the two programs, and the adversary wins if and only if both of these outcome probabilities are greater than gamma. So what are some good properties overall with this testing procedure in our definition? So firstly, as we discussed before, this is a physically meaningful testing procedure, and it has efficient approximate implementations. Secondly, it implies the old definition, which means it is at least as strong as the old definition and has good security, therefore. And finally, it is also a useful tool. It helps the anti-piracy security reductions to go through in our paper and also in a later work that shows copy protection for decryption and PRFs. And this is some detailed technical issue, and please refer to our paper. Next, we discuss how we solve the open question of building copy protection relative to classical Oracle. So firstly, our construction is inspired by the hidden subspace state idea in Aaronson Cristiano's public key quantum money construction in 2012. A hidden subspace is a secreted and random chosen subspace. For example, from an n-dimensional vector space over the finite field of 2, this subspace, hidden subspace A, has only half the dimension, and the elements it contains is negligibly small compared to the whole space. And the subspace state is an equal superposition of all the vectors in this chosen subspace. So it's easy to see that if we perform a measurement on such a state, we get a random vector in the subspace. And if we do a QFT to the state, we would get an equal superposition of all the elements in the dual subspace, A perp. And then we do a measurement, we would get a random element in A perp. And then we define something we call membership oracles. A membership oracle for a subspace A outputs 1 if and only if the input is a vector in A. And finally, our security relies on something we call direct product property. And this property says that given one copy of the hidden subspace state A, and the access to the membership oracles for A and its dual subspace A perp, no polynomial query quantum algorithm can output two vectors, one in A and the other in A perp. Relying on such a direct product harness, we can try to construct our copy protection. The copy protection scheme is very simple. It consists of a hidden subspace state and two oracles, O1 and O2. Oracle O1 parses its input as two parts. It checks if the second part is in subspace A and it's a non-zero vector, and then it outputs Rx, which is a random function evaluation on input X. Oracle O2 also checks if the second part of the input is in A perp, and also it's non-zero, and if so, it outputs Rx, X, or Fx, where F is the function we want to copy protect. Otherwise, both of these oracles should output bot for any vector that's not in A or and not in A perp. So how do we evaluate such a function? It's very simple. First, the user can just input X, which is the input it want to evaluate on, and the subspace state A, and would get Rx. In second step, it can do QFT to the subspace state to get this a superposition of elements in the dual subspace, and then it would get Rx, X, or Fx. Finally, it just XOR the two results together. So how do we prove security? Here we just give a very high level idea of our security proof. Suppose there is some QPT adversary who, when given one copy of the program, produces two programs, F prime and F prime prime, that both function correctly and to compute F. Here we can see that F prime as consisting of a quantum state and access to oracle O1 and O2. Similarly, for the second quantum program, F prime prime, because O1 and O2 can be assumed to be public to anyone. Therefore, these two programs can query them as well. Then we argue that if both these two programs compute F correctly, we can obtain one of the following situations. The first situation says that we can extract one vector in A from the queries of the first quantum program to the oracles. And we can simultaneously extract a vector in A perp from the queries by the second quantum program to the oracles. If this does not happen, then we can use one of these quantum programs to violate the unlearnability of F. In general, we either have to violate the direct product hardness, which we have already proven to be hard, or we violate the unlearnability of F, which is the assumption we use because F has to be unlearnable. Though it seems a very simple high-level idea, actually we need a delicate argument to rule out the possibility that some adversary tries to cheat by making these two programs entangled. So this seems a very clean and simple scheme. Can we just replace our oracle with some cryptography primitives? For example, some obfuscation weaker than VBB obfuscation, like IO. However, a concurrent work by Aaronson and Latvia in 2020 shows that it is generally impossible to do copy protection, assuming LWE and quantum FHE with certain properties. That is, assuming LWE and quantum fully homomorphic encryption with some properties, there is some class of unlearnable circuits that can never be copy protected. So given such a barrier, what can we do? We can set some weaker goals. The first weaker goal is that we weaken our anti-piracy security definition. And the second is we just try to copy protect smaller classes of functions. So for the second goal, this is not the focus of our work. So we'll just discuss some follow-up works. One does copy protection for compute and compare functions in the random oracle model, and the other does quantum copy protection for decryption and PRFs. So let's get back to the first direction. What can we do with the security definition? In the same work by Annes and LaPlaca, they put forward this notion of secure software leasing. Secure software leasing is almost the same as copy protection, except that we have something called malicious pirate and honest freeloader. What does that mean? A pirate who tries to pirate a copy of the program can do anything it wants. However, the users who get these copies of pirate programs, they will follow the instruction by the authentic program. Basically, it follows this algorithm eval published by the vendor. And it does not follow the instructions by the pirate. Even though this weakened security notion is still subject to general impossibility result, it might be easier to give construction for specific functionalities in the plain model without using oracles. For example, Annes and LaPlaca gave the construction of secure software leasing for searchable compute and compare functions, assuming I/O and simulation extractable NISIC. Inspired by this notion of secure software leasing, we bring out a new notion called copy detection. And the main difference between these two notions is that in our definition, we will emphasize the usage of public key in these weakened notions. So what's a copy detection? We also have almost the same algorithms as copy protection. We have this keygen, but the keygen also generates a public key along with the original secret key. And we have this check algorithm. In addition, this check algorithm takes in a quantum program and the public key we generated and output a bit B specifying whether the check algorithm thinks this program is pirated or not. And then also a leftover program after it does the check. Then when we test our anti-piracy, before we even test the functionality of the program, we apply this check using public key on the given programs and output 1, specify that we think the program is actually authentic and 0 otherwise. If the program can't even pass check, we don't even have to test its functionality. Using this security notion, we show that we can achieve public detectable quantum copy detection scheme for any watermarkable functionalities. The security relies on a usage of public key quantum money and also the watermarking property of the functionalities. Many cryptography functions can be watermarked, such as PRFs and PKE and signatures. And for those who are not familiar with watermarking, this is a classical cryptography primitive that allow us to embed marks, unremovable marks, into classical functionalities, so that anyone who tries to remove the mark would destroy the underlying functionality. As we mentioned before, when we compare our security notion with SSL, we mostly emphasize that we emphasize the public detectability of these weaker copy protection notions, even though we restrict the adversary's behavior by asking the freeloaders or asking the testers who test these programs to follow the eval algorithm published by the vendor. This largely restricts the behavior of the adversary. Whereas in the copy protection, adversary is allowed to do anything as long as the quantum program it outputs functions as the original functionality. However, in these weakened security notions, anyone with a public key can detect if a program is pirated or not without even knowing the functionality, since the functionality can only be known by the vendor of the program. And There's a concurrent work that also achieves secure software leasing for PRF using this observation of watermarking and semi-public key quantum money. Some other follow-ups include a work that came out this year that achieves information theoretic secure software leasing for compute and compare functions. That's it. Thank you.